these old abstract films, they were really my inspiration to actually even start thinking about making films. So that's a big link. And I think also when I started to make films, I was really also interested in this idea of making a kind of composition of light in time. Also studied composition for a while, like electronic music composition. So a lot of the sort of techniques or like vocabulary or ideas I learned there, I also started applying to my films. So I think that's also a very direct link. And for me, the biggest difference in a way is that, like gradually, while making more and more films, for me the emphasis of making like this has become sort of obvious for me that that's how you can make a film. And for me, the films I make now also I try to sort of address other things, and in a way I address them in a sort of ambivalent way, because on the one hand I think that these films I make should be able to be consumed without any prior knowledge. Like you should just be able to enjoy the visual experience without knowing anything, how it was made or why it was made or whatever, but just enjoy the pure sensory pleasure, I hope. That's on the one hand side. On the other, it's like for myself, I'm like when I make these films, I'm really thinking about a lot of things, like which for me also are addressed in this film, like what I said about these crystals. Like those are really the things I think about, and which I also hope that in some sort of subtle, non-verbal way will guide your associations or your ideas about these films. And perhaps it's good if I show a bit, I will show some of the backgrounds of the techniques I used. Like this, basically like where does this image come from? And then I will show some related things. Like one source this image comes from, or sort of historical source, is the idea that you can make images with waves. And these pictures are from a book about acoustics. It's Gladny. He did experiments about musical instruments, like why does a violin sound so good, or why does it sound like a violin. And basically, a method he devised is to put sand on a vibrating surface, and then you get patterns which have to do with the frequency you put on this vibrating surface. Then later on, you have a guy called Hans Jenny, who was a Swiss doctor, anthroposophist, and he thought that was the secret of the universe. So these patterns, you find them in zebras, you find them in flowers, you find them everywhere, and he thought it's because everything is based on some kind of vibration. So I have a little clip with Hans Jenny himself explaining how this works.
Hier haben wir die Generatoren. Sie erzeugen die elektrischen Impulse. Diese kommen in die Kristalle hinein und werden zu richtigen Schwingungen. Diese Schwingungen übertragen sich auf die Platte. Dadurch werden diese Schwingungen verstärkt, bekommen eine gewisse Resonanz und dann hören Sie de facto den Ton. Wir wollen noch einmal diesen Versuch Ihnen zeigen, wie eine solche Figur entsteht. Wir streuen den Sand auf die Platte und Herr Stüten schaltet nun eine bestimmte Schwingungszahl ein, oder wie man sagt, eine Frequenz, und Sie sehen, wie der Sand sich formiert, und Sie hören den Ton, welcher diesen Formationen des Sandes entspricht.
Christian Stüten, ein langjähriger Freund der Familie, war von Anfang an als Jennys Assistent an den Experimenten beteiligt. Heute, mehr als 30 Jahre danach, blickt er zurück.
And it's also like this whole idea of images which consist of waves somehow, or patterns of waves. That's of course also has to do with like this idea if you put light waves or some kind of frequency, light of a certain frequency through a crystal or through a structure, you get also this kind of interference patterns. I think another source for the film is like these traditional Eastern ornaments, like Arabic, Moorish, Persian ornaments. And what I liked about these ornaments, I mean, some of them, of course, are just very beautiful. But what I find also interesting about is that in a way they didn't really have a theory about them. They only knew how to make them, like with like very simple geometry, like with a compass and a ruler. You can all these handbooks, they explain how to make them, but not so much what they mean or how they group together. And then from these kind of patterns, at some point, you get Kepler, who's like in the beginning of the 17th century, so like in a way the first who tries to develop a kind of theory about these symmetries and what symmetries are possible and how they work. So you get this kind of excursions into symmetry and theories of symmetry. So that's one also influence, and another one is this book and what started it. This is also a book by Kepler, and it's called what is it called? De Nive Sexangula. It's about the six-angled snow, and basically it's a little book where he tries to find the reason why snow crystals always have 6 angles and never 5 or 7. And then he has a lot of theories, and like I think he has 4 or 5. And then one of them is like thinking, yeah, perhaps it's because water drops are little balls, and if you put all these balls together, then basically what you get is you get a central ball, and you get a kind of grouping around the central ball, and that's why it can only be 6.
But the idea of molecules were not at that time.
No, so in a way. And the interesting thing is that you think, yeah, but that can't be the explanation. So in the end, he says, no, I don't know.
Mm-hmm.
But it is the beginning of crystallography. So the whole idea that you have little particles, and that these particles, the way they fit together, is an explanation for the bigger shape or what these crystals can do. So later you get the same idea, but then by different scientists. So there's also
it's interesting that a lot of speculations in the end are quite.
Yeah, in a way, yeah, and I guess also part of it is that, of course, there's also a lot of speculation which is just really wrong, and we forget about these.
Yes, yes, sure.
So,
but it's good that people speculate.
Yeah. And in a way, this I find also very nice because it also reminds me of pixels. Like there's also a crystallographer from the, I think, early 19th century called Aoui. He's a French crystallographer who really had this idea. Yeah, it's only about crystals are made of a kind of bricks, and how they fit together. That determines the shape of these crystals. So it's really like you have these sort of 3D pixel shapes. And you get all these different theories. And also there's a lot of weird theories, like sort of egg-shaped molecules, or like very complicated systems of how molecules could fit together, because they just had no idea yet about molecules, or reactions, or elements, or whatever. And then basically one of the breakthroughs was this idea, okay, we can, if we shine X-ray light through these things, then we can sort of see how they made. And this is one of the first X-ray patterns. And then from these regularities in that pattern you get, when you shine light through it, they could sort of derive structures, and then you get things like this. And this is basically how we still think crystals work, like it's a sort of regular grid in 3 dimensions, and the way it fit together determines how the characteristics. And then you have this one, which looks perhaps a bit similar to this X-ray things I showed you before. But the funny thing is, if you count these points, you will see that there's 10. And the interesting thing about crystals and all the symmetrical patterns is that there's not so many possibilities. Like if you think about making a floor in your bathroom, you have basically a choice of 3 types of shapes. You can have triangular tiles, and it's going to work. You can have square tiles, that most people have, it's also going to work. And you can have tiles with 6 like hexagonal tiles. That's also going to work. And basically, if you have tiles with 5 corners, it doesn't work, because you get holes. Like it doesn't, you can't actually fit. And crystal in 3 dimensions, like in crystals, it's the same. And at some point, they found this X-ray thing. So they found this material which has some kind of symmetry in 5, which you don't find in, which is not really possible. And then headlines. I mean, I don't know. But then also this image, because that's basically what this image shows, is a symmetry in 5, and that's why it doesn't work. Like that's why you get all these strange holes, let's say. So if you look at it at the first glance, you think, oh, it looks symmetric, but in fact it's not. It's a sort of quasi-symmetric.